Hi everyone. So before I get started on the math for today, I just wanted to mention a couple of quick things. One thing is that I went through and I graded all of the discussions. So basically, you got points if you contributed to the discussions. And I tried to answer any questions that it looks like never ended up getting answered. So if you still feel like you didn't get a question answered, definitely feel free to email it to me. And that's how it will generally work. So usually on Mondays, I'll go through and I'll grade your discussions, and then I'll also just check and see are there any questions that didn't get answered. Um, Maybe just to bring up a couple of things that a lot of people asked about. So, because maybe some others of you are also wondering this. So, one thing that came up a lot was people were talking about, is there a better way to find the slope of the tangent line other than doing this thing of plugging in numbers? And there is, and that's what we're actually going to get to on Friday of this week, and that's something that's going to be a really big topic in this class. So, we kind of like started talking about the idea of tangent lines at the very beginning of the quarter. Now we're doing limits in order to kind of help us build up what we need to return to that idea of tangent lines a little later. And we'll see that yeah, basically, yes, there is definitely a much better way to find the slope of a tangent line. Um, One other thing that came up is that there was a typo on the solutions for, I think it was Friday's worksheet. So a few of you were like, where did that negative sign come from? There was a typo, so sorry about that. One other thing I just wanted to show you. So when you are doing discussions, so there's an option here where it says insert math equation. So if you want, and I don't know how important this is going to be for the kind of stuff that we'll be doing in this class, but you might find it useful. Basically, it just has things like if you wanted to use the letter pi, you can find it wherever it is right here. It has, less than or equal to symbols. It has a lot of stuff that we're not going to be using, but some stuff that you might find useful, infinity, other stuff like that. Um, yeah, I think that's about it for discussions. I guess one more thing I can say is I don't know why you guys haven't posted any animal pictures because my other class has posted four dogs, a cat, and a guinea pig, and they're all really cute. So no pressure, but yeah. Okay, so let's get into the math for today. So we're still going to be in section 2.3 in the book. Um, and we're going to today be talking about something that is called the squeeze theorem. So this is basically, it's not going to be as important as the other methods that we talked about like on Friday and in yesterday's video. It doesn't come up as much, but I just think it's a good, it kind of brings up this idea of comparing functions to each other. And that same idea is going to come up in Calculus 2 and also in Calculus 3. So I think it's kind of a good warm up for that idea of being able to compare functions and apply a theorem to draw conclusions from that comparison. Okay, so I want to start off by showing you an example of a function where you might use the squeeze theorem, and we'll talk about why you can't use the other methods on this example. Then I'll tell you what the squeeze theorem is, and then we'll go back to that example and see how to actually do it. So let's say that you wanted to um, evaluate the following limit. So let's say you wanted to evaluate the limit as x approaches 0 of x squared times sine of 1 over x. So what do we have so far in terms of methods? So one thing that you could do here is you could plug in numbers. But basically, the plugging in numbers method is really not like as official of a method as the other ones that we've been doing. So moving forward, basically, you're only going to plug in numbers in very special circumstances. Generally speaking, you want to use the algebra methods from Friday and yesterday, and then this new idea as well. So aside from plugging in numbers, you might think about, okay, can we do direct substitution? So can we plug in 0 just directly? And no, we cannot. So even though what we have here is, we have x squared, we have a trig function, those are nice functions. However, sine of 1 over x is not defined at x is equal to 0. So we cannot use direct substitution because the function is not defined at x is equal to 0. And then additionally, none of the simplification methods we've really talked about are going to work here. So really, like the problem is that the thing that makes this undefined is the 1 over x, right? But that 1 over x, there's really nothing we can do to simplify that. It's not like we can factor and cancel or anything. It's just 1 over x. And then additionally, it's inside of sine. So it's really like we can't do anything with this function in order to simplify it. So what we're going to do instead, so maybe I'll write that over here. So instead, we will compare this function. So maybe let's call it, I'm going to call it g of x is equal to x squared times sine of 1 over x to other simpler functions and use those functions to evaluate the limit. And we'll see what I mean by that in a few minutes. Okay, so that's kind of what's going on big picture. So let's say what the squeeze theorem actually tells us. So the squeeze theorem, and we'll see why it's called that once I draw a picture. So the squeeze theorem says that if you have a function that is in between two other functions, so if, and I'm trying to remember what colors I wanted to make this match with the graph I'll pull up. I think I'll do it like this. So if you have a function f of x, and that's less than or equal to a function g of x, and that's less than or equal to a function h of x. So basically what's going on here is that we have a function in the middle and it's kind of like sandwiched by these two other functions. So you can think of this bottom function f of x as being like the lower bound and this function h of x as being the upper bound. So the function g of x is in between f of x and h of x. So if you have this kind of a situation, and it doesn't need to be true that g of x is always between f and h, but it does need to be true when you're close to the place where you're taking the limit. So I'm going to add that in. And that's not really going to come up in our examples, but it's just a kind of a technicality to say. So really, it only needs to be true that the function g of x is between these other two functions when you're actually close to a specific x value. So if you have this kind of a situation, and then additionally, the limit as x approaches a of the bottom function, so that's f of x, if that is equal to the limit as x approaches a of the top function, and why not, I'll just use some colors here. Oops. So if the bottom function and the top function have the same limit as you approach a, so let's say they're both equal to some number L, well, what that tells you is that this other function that is right in between them, it has to have that same limit. Because one of them is supposed to be above, one of them is supposed to be below. This one that's in the middle is kind of squeezed into having the same limit. So what the squeeze theorem tells you is that then the middle function, so the limit as x approaches a of the middle function is equal to that same number. So what would this look like kind of graphically? So we'd have a situation where you have your top, or maybe let me draw a middle function first. So maybe you have a function that looks like something like this, something weird. And then you have another function, f of x, which is below it. So maybe let's do it like, I was trying to draw this a little differently than I did. No, that's fine. Okay, so I'll do this like this. So let's say this function is above, and then, or sorry, this is backwards. My color coding is wrong. So f of x is supposed to be the function below. Sorry about that. So let's say you have this function that's below, and then you have this function that is above. And I didn't draw this perfectly. This would also go down to 0. But basically, so let's say you're taking the limit as x approaches 0 of these different functions. Well, the limit on the top, it looks like as you get closer to 0, the red function is going to a height of 0, right? And for the green function, as you get closer to 0, the green function is also approaching a height of 0. So this middle function, because it's being squeezed between them, or this is actually also sometimes called the sandwich theorem. So because that middle thing is being sandwiched between the top and the bottom, it's forced to have that same limit. So why is this useful? Why would you use this? Well, if you can find functions f of x and h of x that are simpler functions where you can actually find the limit, then it can help you find the limit of something you otherwise would not be able to. So let's go back to our example we had above. So the example we were working with was the limit as x approaches a of, and let's call our function, or I'm going to use blue because it's going to be our middle function. So our function was x squared times sine of 1 over x. And so basically, let's call that function g of x. G of x is equal to x squared times sine of 1 over x. So our goal is going to be to find two functions. So find functions f of x and g of x such that our function g of x, and sorry, I keep making mistakes today, so let me make this actually h of x, because g of x is what we're calling our blue function. So we're trying to find functions f of x and h of x such that our function is in between those two functions. And then additionally, we also need it to be true that the limit as x approaches, and sorry, I wrote x approaches a here, but we're really looking for the limit as x approaches 0. So we also need it to be true that the limit as x approaches 0 of the bottom function is the same as the limit as x approaches 0 of the top function. Because if that's true and we can find what that limit is, then we'll know that our function g of x has the same limit. Okay, so we're typically going to be using the squeeze theorem in situations very similar to this one involving trig functions, because there's a nice fact that we can use about trig functions. So anytime you have sine, so I'm going to write this in terms of sine, but we'll do an example in when we're done with this one using cosine, and it's also true with cosine. If you have sine of anything, like I don't care what you put inside of those parentheses, anytime you're taking sine of anything, your answer is always going to be between 1 and -1, right? It's not possible for you to take sine of a number and get something that's bigger than 1 or less than -1. Because the way that the sine function works, it just doesn't make sense. If you think about how you calculate sine and you're on the unit circle, it's just, you're never going to get an answer that is bigger than 1 or smaller than -1, no matter what you're putting inside those parentheses. So specifically for our example, well, we know that sine of 1 over x is always going to be between 1 and -1. And the same thing would be true if it was sine of 5 over x, or sine of 300x, or sine of x squared over 5. It doesn't matter what's inside the parentheses, but in this specific case, we have sine of 1 over x. So we can say that sine of 1 over x is between 1 and -1. However, that's not our entire function. Our function is x squared times sine of 1 over x. So we need to figure out if sine of 1 over x is between -1 and 1, what does that tell us about x squared times sine of 1 over x? So there's a couple of ways to do this, but one way that you could think about it is when you have an equation or an inequality, you can multiply both sides by the same thing and it's still true, right? That's kind of basic equation or inequality solving. So in this case, we can take this entire inequality and we can multiply everything by x squared. The one thing that you have to be careful about is when you have an inequality, the signs will flip direction if you multiply by a negative number. But if we're multiplying everything by x squared is always positive or greater than equal to 0, right? Because x squared, squaring gets rid of negative signs. So what we're going to do is we're going to multiply this entire thing by x squared. And so what are we going to get? In the middle, we'll get x squared times sine of 1 over x. And then on the right, so when we multiply 1 by x squared, that will become just x squared. And then when we multiply by x squared on the left, we'll get negative x squared. So we just found our two functions. Sine of 1 over x times x squared is always going to be between negative x squared and positive x squared. And basically, you can just think of it as like the x squared is kind of the main part of the function. And then this part, the sine of 1 over x, that kind of just multiplies x squared by a number. And the number it's multiplying it by is always going to be between negative 1 and 1. So it's never going to cause x squared to get to, or it's never going to cause x squared times sine of 1 over x to become bigger than x squared or smaller than negative x squared. So it's truly bounded by this function in red and the function in green. So we just found our top and our bottom function. So we just figured out that our bottom function is f of x is equal to negative x squared, and our top function is h of x is equal to positive x squared. So now what we need to verify is we need to check whether this is true. So here we said it also needs to be true that their limits are the same in order for this to work. So let's try that. So if we take the limit as x approaches 0 of our bottom function, so negative x squared. So now we might be able to see why is this, a better function than the one we started with. Well, we can actually just evaluate this limit by plugging in 0, right? We could not plug 0 into this function because you would get something undefined. But what we did is we found this kind of stand-in function, or these two different stand-in functions that that we can plug 0 into. So if we plug 0 into this lower function, we get 0, right? If you plug 0 into negative 0 squared, you get 0. And then if we plug 0 into positive x squared, so that's our top function, you also get 0. And so what does that tell us? So that tells us that our middle function, because it's in between these two things, it has to also be true that the limit as x approaches 0 of our middle function, which was x squared times sine of 1 over x, that has to have the same limit. So the limit of that function is also equal to 0. And we'll pull up the graph of this in a second. But just to kind of point out, what I think, so every time I teach this, students have kind of a harder time with this than I would expect. And I think a lot of it is that it's very different from other stuff. You're not just kind of doing algebra, crunching numbers, plugging things in. You have to kind of do some reasoning. And the steps, I think, are a little bit different than what you might kind of expect for a math problem. So what are the important steps here? So the important steps are kind of two things. It's basically what's written up here. So the first important step is that you have to figure out what are those two functions. So you need to find your upper and your lower function and declare what those are. If you're doing a problem using the squeeze theorem and maybe let's say I put this on the quiz for this week, I would need to see you telling me explicitly what that top and bottom function are. And the way that you usually find them is basically what we did here. And we'll do another example in a little bit, but usually we're dealing with trig functions. And so you're starting with the fact that sine is between negative 1 and 1, and then you're using that to come up with your final answer. So that's the first thing, is coming up with those functions. The second step is you need to show that the limit of the bottom one and the limit of the top one are the same answer. So you need to actually find the limit of the bottom function, find the limit of the top function, explicitly write those down. And then you can conclude that the limit of the middle one is the same. So typically when I give these problems on like tests and quizzes and homeworks and stuff, a lot of students, you have the right ideas, but maybe you're not kind of writing all the steps out. So make sure that you write those steps down when you're doing this. So let's look at what this looks like graphically. So this is what the graph of sine x squared times sine of 1 over x looks like. So notice that it gets really squiggly in the middle. Basically, as you get closer and closer to 0, it actually gets like more and more squiggly. And let's see, I'm not sure. That probably just makes it harder to see. So our bounding function, so our top function was just x squared, and so that looks like that. And our bottom function was negative x squared. And so what we can see is that the function x squared times sine of 1 over x is truly squeezed between these two functions. And so all three of them head towards 0. Okay, so let's do another example. So this other example is going to bring up one more kind of trickier, or not trickier, but one more step. So let's say we wanted to evaluate the following limit. So we're going to look at the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1 plus 5x. So what I would say when you look at this is that there's kind of two parts to this limit. So the first part is what's here. And this actually looks really close to what we were just working with in the other example, right? The other example we had, it was x squared times sine of 1 over x. And this is x minus 1 squared times cosine of 1 over x minus 1. So it's that same kind of format where you have sine or cosine of 1 divided by something, and it's undefined when you try to plug in the number where you're taking the limit. So what we're going to do is we're going to end up using the squeeze theorem on that part of the limit, but we actually want to deal with this 5x separately. And so this goes back to one of the rules that I wrote down at some point last week. It was one of the rules I was like, we're not going to use this that often, but this is one of the cases where we actually use this. So one rule that exists about limits is that, so if you're taking the limit as x approaches some number a, and maybe let me use different letters for this function so it doesn't get mixed up with the squeeze theorem. So I'm just going to call our functions m of x and n of x. So if you're taking the limit of a sum of two functions, that's the same thing as taking the limit of one part of that and then adding that together with the limit of the other function. So basically what this rule says is that you can, if you have a limit where things are split up over addition, you can split that limit up. So what that means is that we can take our original function up at the top. So the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1 plus 5x. Instead of evaluating that all as like one item, what we can do is we can treat it as two separate things. So we can first try to figure out what is the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1. And then I might be running out of space here, so let me scroll a little bit. And then individually, we can take the limit as x approaches 1 of 5x. And kind of deal with those as two separate problems, and then at the end, put them back together. So how would we evaluate this, this second part? Well, this one we can actually just plug in 1, right? So the limit as x approaches 1 of 5x, this part is actually just equal to 1. So on this part, we can use direct substitution, because you can just plug in 1 and we end up getting that this part of the limit is equal to 5. So we're going to focus now on the other part, and then we'll add in 5 at the end. Okay, so this other part, let's call this function here g of x. So this is going to be the function that will be squeezed in the middle of our squeeze theorem. So we have g of x is equal to x minus 1 squared times cosine of 1 over x minus 1. So how do we know that this is a squeeze theorem problem? Well, again, we can't plug in 1, and there's no algebraic simplification we can do. So what we're going to do is basically something very similar to last time. So just like how sine of anything is always between -1 and 1, it's also true that cosine of anything, so in this case, cosine of 1 over x minus 1, that is also going to be between 1 and -1. So in this case, the function that we actually want to have something to compare with is not just cosine of 1 over x minus 1, it's x minus 1 squared times cosine of 1 over x minus 1. So just like how in the last example, we took this entire thing and multiplied it by x squared, in this case, we want to take this whole thing and multiply it by x minus 1 squared. So what we'll end up with in this case is, so in the middle, we'll have x minus 1 squared times cosine of 1 over x minus 1. And that was our goal. And then on the right-hand side, we'll end up with x minus 1 squared because we're just multiplying 1 with x minus 1 squared. And then on the left-hand side, we'll have negative x minus 1 squared. So we found our two bounding functions, right? So now we know that if f of x is equal to negative x minus 1 squared and g of x is equal to positive x minus 1 squared, then we just found that g of x is in between f and h. So f of x is less than or equal to g of x is less than or equal to h of x. Okay, so the next thing we need to show is we need to find the limits of each of these things. So if we take the limit as x approaches 1 of the bottom function, so negative x minus 1 squared, again, we can just use direct substitution, right? Because we can just plug in 1. And so if we plug in 1, we get negative 0 squared, so that's just 0. And so here or for the top function, same idea. We plug in 1 into just x minus 1 squared, and that's 0 squared. So again, we get 0. And so because we got the same answer for the top and the bottom function, that forces our middle function to also have the same limit. So the limit as x approaches 1 of our middle function times cosine, and I'm definitely going to go off screen here, so let me just shift this. So that limit is going to also equal 0. Okay, so that's not our final answer though, right? Because our original function was kind of two parts. So basically we had our second part, our 5x, that limit equaled 5. And so putting those together, we get that the limit as x approaches 1 of x minus 1 squared cosine of 1 over x minus 1 plus 5x. So we got 0 for the squeeze theorem part. And then we got 5 for the other part. And so that all together gives us a final answer of 5. So that's the squeeze theorem. Let's look at the graph real quick. So I'm not going to pull up the graph with the plus 5x part because that isn't really, we can't really look at that through the eyes of the squeeze theorem. So let's just look at the middle or the function without the. That's weird. Why is nothing showing up? I zoomed in too much, maybe. Yes. Okay. So let's just look at the function that we actually did the squeeze theorem on. So it basically looks very similar to the other function we had. It's just that it is shifted over to the right. And so if we look at positive x minus 1 squared, we see that that's always above. And if we look at negative x minus 1 squared, we see that that's always below. And so as we get closer and closer to 1, the top and the bottom function are also both going to 1. And so that means that the blue function in the middle goes to 1 as well. All right, so that is it for today. I thought this would be a slightly shorter video. I'm not sure if it really came out to be. But tomorrow we're going to talk about continuity, so functions being continuous, and that will be kind of a shorter topic. And then we'll talk about a slightly different type of limit. And then finally, we'll get into derivatives on Friday. So thank you, and I will see you next time.